Um, Good afternoon, everyone. Welcome to today's class. Um, in the last class, I mentioned that um, for the following two lectures, we are going to answer questions about um, previous lectures or previous homework questions. So in today's class, I want to use today's lecture to uh, go through questions in the homework 5, which is due on uh, this uh, this this Friday or next Monday. Should be next Monday. Yes. Um, so without further talk, let's get started. The first problem, it asks you to convert the following decimal numbers to binary numbers, right? And there's a very important hint here, which says for integer parts, we can use repeated division by 2 method to convert the decimal number to binary number. And for the fractional parts, we can use the successive multiplication method, right? Uh, I will do the first question as the example to show you guys how to convert a fractional decimal number to the fractional binary number. Okay, right. So as the hint claims, for the integer part, which is 120, this is a decimal number, right? And to find the corresponding binary number of a decimal integer number, we can use successive division by 2 method, right? So we divide 120 by 2, which gives us result is 60, and the remainder is 0. And we divide 60 by 2, we got 30, remainder is 0. 30 divided by 2, result is 15, remainder is 0. And 15 divided by 2, result is 7, and the remainder is 1. 7 divided by 2, we have result is 3 and remainder is 1. 3 divided by 2, result is 1 and remainder is 1. 1 divided by 2, result is 0, remainder is 1, right? So after we have 0 in the result, we can stop divide the result, right? And the binary representation of the original decimal number is hidden in the remainders. So, and the order of this binary number is from the bottom to the top. So that will be 11111000, right? So that's the integer part, 11111000. There's one point I want to emphasize, which is this is an unsigned binary number, right? Which means the first one doesn't mean this is a negative number. This is just an unsigned negative number, which means it is neither positive or negative, right? It's an unsigned binary number. All right, so that's the integer part. We also want to find what's the fraction part, binary representation. And to finish this job, we need to do the successive multiplication by 2, right? So we first multiply 0.25 by 2, and we have 0.5. And then we record the integer part, which is 0, and put the fraction part in the second multiplication. And we got 1.0. And when we have 0 in the fraction part, we stop. And the integer part for the second multiplication is 1, right? And the order of this fractional binary number is from top to bottom, which means 0.25 is 0.01 in the fractional binary number, right? All right, the last step we need to do is to combine these two representations together, and the final representation of 120.25 is 111100.01. Right. So that's how we handle the conversion between the unsigned decimal number to the unsigned binary number, right? All right, for the second question, I think after I show you this example, you can handle the second problem, right? All right, so let's continue to problem number 2. In this problem, we need to convert following numbers to 8-bit signed binary numbers, right? So here the keyword is signed binary number. All right, so I will do problem 1, okay? And for the following 2 problems, you can follow my procedures. All right, so for signed binary numbers, first, this is a negative number, right? Minus 15 is a negative. It's a negative number. And there are 3 steps to write a negative binary number. The first step is we need to write the unsigned binary number. The unsigned binary number, right? Which means we have we have 15, and that is 1, 1, 1, 1 in the binary form, right? We can use the quick way to find the binary representation of 15, which is 8421 method. From 15, we need to sum 8 and 4, which give us 12. And 12 plus 2 is 14. 4 plus 1 is 15, right? So we need these 4 digits, which give us 1111. And then we write the positive binary number, which means we need to add a 0 in front of the unsigned binary number. And then we flip the bits, which means when we have a 0 in the binary number digit, we flip that to 1. And when we have 1, we flip that to 0, right? And that's the result after the flipping. And the third step is we just need to plus 1 with the flipped positive binary number. With the flipped number, and we got 10001, right? And that is the minus 15 in the decimal form. We can verify that by converting this binary number back to the decimal number. And the method is we need to first count positions of each digit, and starting from right to left, and starting from 0, right? So here the position of this digit is 0, 1, 2, 3, 4, right? After we figure out this point, we can decode this binary number by using this method. The first digit 1 is minus 1 times 2 to the power 4, because this is a signed and a negative binary number, right? And then all other digits are 0, so we can ignore that. The last one is 1 times 2 to the power 0, and then that equals to minus 16 plus 1, which is minus 15, right? So this representation is correct. Right, after we find minus 15, this is a 5-bit negative binary number, right? And we want to find an 8-bit binary number. So we need to add 3 ones in front of the original representation. And now we have together is an 8-bit negative binary number, right? For other 2 questions, the procedures are the same with the first example, with the first question. So you guys can follow my procedures to figure out the following 2 questions. Okay. All right, let's continue to the next one. In problem number 3, it's a binary summation problem. There's only one question I want to emphasize is the overflow problem. The overflow means when you have an increment, when the the summation result is has a larger size than the two summation numbers, then we have an overflow. So what that means? That means, for example, if you have 1 0 plus 1 1, the result is 1 0. I'm sorry, 1 0 1, right? And you see, the result is 3-bit. For these two summation numbers, they are both 2-bit. So this bit, the extra bit, is the overflow. Okay, so back to this problem, we have 1 0 1 0 0 1 plus 1 1 1 0 1 0, right? When you do the summation, you do the summation bit by bit. The first bit is 1 plus 0, the result is 1. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1, the result is 1 0, right? Which means we have an increment for the previous bit. And then 1 plus 0 plus 1, the result is 1 0, and we have increment for the previous bit. For this digit, for the last one, is 1 plus 1 plus 1, the result should be 1 1, right? And we have an extra bit on the result, and that's the overflow. So for this problem, the answer is yes, and we have overflow on the in the summation result. Okay. All right. For problem number 4, we already talked about this problem in the lecture, right? So if you guys have questions about these two problems, you can go back and check the lecture questions, and the lecture should be let me give you the title of the lecture note. Okay, see lecture on April 13th. Alright, for the last problem, it's a logic simplification and implementation problem. So we have this logic exploration. The principle we need to use in this problem is the De Morgan's law. Okay. Is the De Morgan's law. Okay. De Morgan's law says when you have a plus c, that equals to a bar times c bar, right? Break the line, change the sign. So here f equals to ab times a plus c together bar plus ca bar, right? So when you have a plus c bar, you need to break the line here and change the sign. And the result is going to be a bar times c bar plus ca bar. And after you apply the De Morgan's law, we have a times a bar, which equals to 0, right? And after you have a 0 in the multiplication, the final result is always, the final result of the multiplication is always gonna be 0, right? So the final result is 0 plus ca bar, and that is just ca bar. And when you draw the logic circuit, you need you need A as input, you need C as input, and B, the input B is ignored, right? And you need A bar, which means you need a NOT gate, and you need to multiply these two inputs together to get F, okay? All right, so that's how we handle problem number 5. So that's all about homework 5, and because I didn't receive any questions from you guys about questions for previous lectures or questions for the homework questions, so you still have chance to ask questions. In the next class, we will also answer questions. If you have any I will make a video to answer these questions. And if don't, you can also send me your questions by emails. Okay. All right. So don't forget the due date for homework 5 is on next Monday. And if I won't receive any questions by the next lecture, then I will talk about the final exam. Okay. All right. I'll see you guys in the next time.